Dear friends, now we are going to discuss the different numericals on this particular engine testing and the performance analysis. We have already discussed the different things regarding the performance evaluation of an internal combustion engine. Now we are going to discuss the different numericals on this particular engine testing and the performance analysis. So with the help of this particular example, we are going to discuss the different varieties of numerical on this particular topic. So let us consider the statement of the problem is given. The trial reading on 4-stroke single cylinder engine are, suppose there is one 4-stroke single cylinder engine is there and there is one trial readings taken and these are the different readings. The first one, that is trial duration is equal to 30 minutes, oil consumed is equal to 4 liter, calorific value, that is nothing but CV, is equal to 43 megajoule per kg. So this mj is nothing but megajoule per kilogram. Specific gravity of fuel is equal to 0.8. Indicator diagram area is equal to 8.5 centimeter square. Length of the diagram is given is equal to 8.5 centimeter. Spring constant is equal to 5.5 bar per centimeter. Brake load is equal to 150 kilogram. Spring balance is equal to 20 kilogram. Effective brake wheel diameter is given, that is 1.5 meter. Speed is equal to 200 rpm. Cylinder diameter is equal to 30 centimeter. Stroke length is equal to 45 centimeter. Jacket cooling water is equal to 10 kg per minute. Temperature rise is equal to 36 degrees Celsius. So much data is given in this particular problem, and according to this given data, we have to calculate the brake power first, then the indicated power, the mechanical efficiency, then the BSFC, that is brake specific fuel consumption, then the indicated thermal efficiency we have to calculate, then after we have to calculate the brake thermal efficiency, then the heat carried away by the coolant. So these things we have to calculate with the help of this given data. Okay, so generally we know for 1 liter is nothing but 10 raised to minus 3 meter cube. So these things are required for solving the problem. So this is about the convergence of the unit. So according to the given data, we have to write the things in the given data. So the calorific value of the engine which is given in the problem, that is 43. So we start with this one. The calorific value is given, that is 43 megajoule per kg. So we have to convert it into kilojoule by multiplying 10 raised to 3. So calorific value is equal to 43 into 10 raised to 3 kilojoule per kg. Then after the load is given, the two types of loads are given in the problem. One is a brake load, that is equal to 15 kg, and another one, that is a spring balance load, that is equal to 20 kg. So the units are very essential, and with the help of this unit we can understand these things are for the load which is given in the case of this particular engine trial. So 150 kg, let us consider W1, that is for the load 1, W1 is equal to 150 kg, and another load, that is W2, it is given in the problem, that is 20 kg. So also the speed of the engine is given, that is 200 rpm. So the speed of the engine which is given in the problem, that is speed, and let us consider capital N stands for the speed of the engine, that is 200 rpm. The diameter of the engine is also given, that is 30 centimeter. So this is about the cylinder diameter, and which is given as 30 centimeter. So after that the stroke length is also given 45 centimeter. So this is about the stroke length that is given in the problem, 45 centimeter. So write this thing in the given data. So the mass of cooling water which is also given in the problem, and that is equal to m suffix w. So this is given in the problem, the jacket cooling water. So jacket cooling water is equal to 10 kg per minute, means this is nothing but the mass of the cooling water m suffix w is equal to 10 kg per minute. So write down that things also. So the temperature rise is given. So the meaning of the temperature rise is nothing but the difference between the higher temperature minus lower temperature. So let us consider the maximum temperature in this case, that is equal to T2, and the initial temperature is T1. That's why the T2 minus T1 is nothing but the temperature difference, or we can say the temperature rise, that is given 36 degree Celsius. So with the help of this we can understand temperature is rise is nothing but the difference between the high temperature and the initial temperature. So this is T2 minus T1 is equal to temperature rise, and that is equal to 36 degrees Celsius. So similarly in this case, as we have already discussed, the value of Vn is 200 rpm and the value of K. So we know the value of K for 4-stroke engine is 1/2, and for the 2-stroke engine the value of K is equal to 1. So this is according to the revolution of the crankshaft. So in the case of 4-stroke engine, because in the problem the 4-stroke single cylinder engine is given, so for the 4-stroke engine the value of K is always 1/2, because there is only 2 revolution of the crankshaft. So we can consider this value is 1/2, and generally we have to consider the RPM which is given in the problem. So further calculation will discuss about this value. So similarly the next thing is given, that is this capital D is equal to 1.5 meter. This D is nothing but this particular effective brake wheel diameter is given in the problem, and that is 1.5 meter. So later on we will discuss the use of this particular effective brake wheel diameter while solving the problem. So similarly, after this capital D which is given as 1.5 meter, then we can calculate the area of the cylinder. So how we can calculate the area of the cylinder? So general formula of the area, that is equal to pi/4 d square. So in this case the small d value is given, that is 30 centimeter. So convert it into meter, and we can put the value in this equation, and we can get the area which is equal to 0.071 meter square. So please check this value with your calculators. So after this one, after writing all the given data thoroughly, understanding the given data thoroughly, so now we are going to calculate the different things. So the first unknown, that is the brake power. So we know the formula of brake power. The brake power is given as we already discussed this particular different parameters of an engine, and we discussed the different formulas of this particular performance parameter. So here we have to calculate the brake power of the engine. So we know the formula is 2 pi nt by 60 into 1000, and the answer will come in unit kilowatt. So in this particular case, the RPM of the engine is given, and unknown thing is that the torque. So we have to first calculate the torque in this case. So we know the formula of torque. Torque is nothing but that load into the radius. In this case, W into R. R is nothing but that particular perpendicular distance from the brake wheel diameter. So in this case, the brake wheel diameter is given, that is 1.5. So we know the 1.5, that is the brake wheel diameter, is given in this particular problem. And if you want to calculate the radius, so how we can calculate the radius? Diameter by 2, and this is about the W. So the torque is always in Newton meter. So the load is given in terms of kg. So we have to multiply that particular load into the Newton by multiplying 9.81. So again the two types of loads are given. One is 150 and another one is a 20. So this load is nothing but the brake load and the spring balance. So average load, or rather average load, we have to calculate first the required load in this case, or the available load in this case, that is coming like 150 minus 20, that is W1 minus W2. So in such kind of a problem we have to calculate the load like W1 minus W2. This is about the load, because the two loads are given, 150 minus 20, then it will come 130 into 9.81. This 9.81 is required to convert that kg into in terms of Newton, and we will get the load in terms of Newton itself, and multiply by this d by 2, that is nothing but the radius. So put all the values, and finally we can get the torque is equal to 956.48 Newton meter. So please do the calculations with your own calculator and check down this particular answer. So after getting the value of torque, now we can put the value of torque in this equation of brake power. So 2 into pi into RPM is given, that is 200, into the calculated answer of torque, that is 956.48, divided by this 60 into 1000 as it is, and we can calculate the brake power, which is equal to 20.03 kilowatt. So this is the first unknown, and this is the answer of brake power, that is nothing but 20.03 kilowatt. So I am requesting you to please do the calculation at your home for the practice purpose. Use the calculators for calculation of these particular things. So after this one, the second unknown, that is nothing but the indicated power. So we have the formula of indicated power again, this N into P suffix Mi into L into A into N into K into 10 by 6. Okay, so in this case the different things are again given in the problem. This stroke length is given, area we have calculated, the RPM is also given, then the value of this particular K we can write them into 10 by 6. So the unknown thing which is present in this particular problem, and that is nothing but called as the PMI, because this N stands for the number of cylinders. So in this case the number of cylinder is 1. So again the value of this particular number of cylinder, which should be 1, and I am writing over here that value is equal to 1. So this is that particular number of cylinder which is given in the problem, that is equal to 1, and this is about the RPM of the engine, that is equal to 200. So please we have already written the value of RPM over here, so there is no need to consider this particular thing over here. Only you can consider the number of cylinder in this particular problem which is given, that is equal to 1, because it is already mentioned in the problem, 4-stroke single cylinder engine. So this small n stands for the number of cylinders which are given in the problem, that is equal to 1. So please consider these things. So after this one, the next thing is what? Now the unknown in the case of indicated power, that is P suffix Mi. So this P suffix Mi is nothing but called as the mean indicated pressure in terms of indicated power. So we have the formula of mean indicated pressure. Its standard formula is area of the diagram divided by the length of the diagram into spring constant. So these things are given in the problem. Now we are going to use that particular term to get the answer of this mean indicated pressure. So we have the value of area of the diagram which is given in the problem. So the area of the diagram which is given, which is mentioned in the problem, that is 8.5 centimeter square, and the length of the diagram is also given 8.5 centimeter, and spring constant is also given 5.5 bar per centimeter. So dear friends, please remember these units, and the unit conversion is very important task to solve this kind of a problem. So this is 8.5 centimeter square, the length of the diagram is only 8.5 centimeter, and spring constant is 5.5 bar per centimeter. So we can write these given values, area of the diagram 8.5, length of the diagram, that is 8.5, again the spring constant is given 5.5. So here we have multiplied few things. So the area of the diagram is given 8.5 bar per centimeter square. So if you see over here, the indicator diagram area is given 8.5 centimeter square. So we have to convert this thing into the meter itself. So whenever centimeter square is given in the problem and we have to convert into the meter, then we can get to calculate by multiplying 10 raised to minus 4. So 8.5 into 10 raised to minus 4. So that particular centimeter will convert into the meter term. The centimeter square is there. That's why there is a need to multiply by 10 raised to minus 4. And similarly, the spring constant which is given, that is 5.5 bar per centimeter. So again here is the need to convert it into meter by multiplying 10 raised to minus 2. So by multiplying 8.5 into 10 raised to minus 4, that centimeter square will convert it into meter, and similarly for this 5.5 bar per centimeter, then it will come by multiplying 10 raised to minus 2 in terms of meter. And similarly the length of the diagram is also in centimeter, so just multiply by 10 raised to minus 2, so the answer will come in terms of meter itself. And finally, after calculations, after the unit conversion simplification, you come to understand the answer will be 5.5 bar. So the things are there, and the final unit is remaining over here, and that is PMI, that is mean indicated pressure, is equal to 5.5 bar. So the meter and meter will get cancelled over here, only the remaining thing is bar. So here the unit is only 5.5 bar itself. So similarly we can put the calculated value of the suffix mi in this indicated power formula. So just put the particular values in this above formula. So we have the values. The value of n is equal to 1 as it is given in the problem. Number of cylinder is 1. PMI, that is calculated value, is 5.5 into the stroke length of the engine, which is given in the problem. Again, this is the in centimeter, 45 centimeter converted into meter. So multiply by 10 raised to minus 2. The area which we have already calculated, the area which already calculated, that is equal to 0.071. It is already in meter square, so put that area is 0.071. Then after the next one, that is the RPM is given n, and this value is 200 into the value of the K is nothing but 1 by 2. So as we already discussed, the for 4-stroke engine the value of K, that is for the 1 by 2 for 4-stroke engine. So this 1 by 2 we have written over here. So 1 by 2 we have written over here, and this is about that particular 10 which is remaining. So again this 6 as it is, we have to write this 1 by 2, this is for that value of K. So after calculations you come to know the indicated power will be 29.29 kilowatt. So this is about the second unknown in this particular problem. So after this one, now we are going to calculate the mechanical efficiency. So how we can calculate the mechanical efficiency? The mechanical efficiency is equal to brake power divided by indicated power multiplied by 100. So here we have just calculated the brake power is 20.03 something, and the indicated power is this 29.29. So put that value is 20.03 and 29.29 multiplied by 100, and that would come the mechanical efficiency is equal to 68.4%. So this is the efficiency, that's why this is always in percentage. So this is the third required answer in this problem. So after this one, now here we are going to calculate the BSFC value, that is brake specific fuel consumption. So again we have the formula, mass of fuel divided by brake power, and its unit is kg per kilowatt hour. So dear friends, everywhere the units are very important. If you miss to write this particular unit, definitely you will lose some marks, and if you are writing the wrong unit, definitely the further things will be also wrong. That's why the correct units we have to write while solving the numerical. So then after we will get the correct and required answers. So in this case, the formula of BSFC is mass of fuel divided by brake power. So in this case, we have already calculated the value of brake power meter. So we don't know what is the value of the mass of fuel. So how we can calculate the mass of fuel? So again here we have the formula of the mass of fuel in terms of kg per hour. So this is the standard formula. As we have this particular formula, oil consumed per liter divided by its duration into density of fuel. So with the help of this formula, we can calculate the mass of fuel. I am repeating this formula, oil consumed per liter divided by duration into density of fuel. So in this case, the density of fuel would be 800 kg per meter cube. So in this case, the density is given as it is in terms of that particular specific gravity, that is equal to 0.8. So As we know, the specific gravity of fuel is 0.8, so multiply by the 1000, then we can get the that particular specific gravity is in the terms of the density, that is equal to 800 kg per meter cube. So again, we know 1 liter is equal to 10 raised to minus 3 meter cube. So as we discussed earlier, this particular unit conversion, now here is the use of this particular thing. So how we can calculate the mass of fuel? Oil consumed per liter. So in this case, the oil consumed, which is given in the problem, that is the first thing which is given in the problem. Oil consumed, it is equal to 4 liter. So that is in terms of liter itself. So put that particular 1 liter is equal to 10 raised to minus 3 meter cube. That's why convert that liter into meter cube. So that would be 4 into 10 raised to minus 3 meter cube divided by the duration. So for what duration this test was there? So again, the duration or the trial duration is given, that is 30 minutes. So convert this particular 30 minute into that particular, if you can say, that is divided by the 60, and then we can get the answer in kg per hour. So this is about 30 divided by this particular 60 and multiplied by this particular density of fuel, which we have calculated 800 kg per meter cube. So this is oil consumption 4 into 10 raised to minus 3 meter cube divided by the duration, that is 30 divided by 60. This is for hour basis. So multiply by 800, and finally we can get the mass of fuel, which is equal to 6.4 kg per hour. So put the value of mass of fuel in this equation. So after putting the values in the BSFC formula, we can get the final equation of BSFC, that is equal to 0.3232, or we can say brake specific fuel consumption is equal to 0.32 kg per kilowatt hour. So this way we can calculate the value of BSFC. So after this one, the fifth unknown is indicated thermal efficiency. So how we can calculate indicated thermal efficiency? Again, in terms of indicated power, we have the formula of indicated thermal efficiency. Indicated power divided by mass of fuel into calorific value. So here I have written the term, or this particular term is multiplied by 3600. Why there is a multiplication by 3600? Here we are going to understand. So this is because of the unit conversion. So we know the indicated powers unit is the kilowatt. We know the mass of fuels unit is kg per hour. We know the calorific values unit is kilojoule per kg. So just written over here this particular unit in terms of this particular formula. So when we are going to see the unit conversion, this kilogram and this kilogram will get cancelled. So what is remaining? This kilowatt divided by kilojoule per hour. So the watt is nothing but joule per second. So we can write this kilojoule per second instead of kilowatt, and again this kilojoule per hour, when come to the this numerator term, then the hour will be there and divided by this kilojoule. So we can write in the form of the equation, finally this kilojoule and this kilojoule will get cancelled to each other. If you see like this kilojoule and this kilojoule will be cancelled to each other, and only the remaining term is what? Hour per second. So we know hour is nothing but 3600 or 3600 second is nothing but called as the hour. So this second and this second would cancel to each other. So what is only remaining? The remaining term is only 3600. So there is a need to multiply the term with this 3600. I hope you understood this unit conversion, and this unit conversion is very important to solve such kind of a problem. So after this one, now finally after putting the different values, we have the indicated power, we have calculated the mass of fuel, we have the value of calorific value which is given in the problem. So put all the values and just multiply it by 3600, then we come to know the indicated thermal efficiency is equal to 38%. So in the similar way we can calculate the brake thermal efficiency. Only what is the change in the formula? Instead of indicated power, here only we have to write the brake power into mass of fuel into calorific value. Again, there is a need to multiply by 3600 according to this particular simplification. So finally, after calculations, you come to know the brake thermal efficiency is equal to 26.35%. So finally, we are going to proceed to calculate the heat carried away by coolant. So we have the standard formula as we already discussed, mass of cooling water into, that is the Cw into T2 minus T1. So all these things are given in the problem. What is that mass of cooling water? M suffix W value which is given in the problem, that is equal to 10 kg per minute. So that value is again given in the problem itself, and that value which is present in the problem. So after this one, the next one, that is Cw, we have to put the value of that Cw over here, and T2 minus T1, that is nothing but the temperature difference, and after calculation we can come to know the answer would be 1509.8 kilojoule per minute. So I hope you understood this particular thing thoroughly. So even though the given data is look like or the different things are given in the problem, but the methodology is very simple to get the solution. So there is no need to afraid such kind of a problems. Only there is a need to understand the given data, and according to the given data we can get the required answer. So everything is given in the problem. Sometimes the few things are not given in the problem itself. That time we have to consider few things. So that is again essential in this particular case, and according to the given data we are able to calculate the required answer. So whatever things are given in the problems, and according to that problems statement we can use that data and we can get the required answer. So in this case the mass of the cooling water is given, directly put that value. If this value is not given in the problem, so don't consider this, and the T2 minus T1 is also given, and sometimes the specific or we can say the mass of cooling water, and this value of this specific heat of water is also sometimes mentioned. If it is mentioned, then we can use over here and we can get the answer, and that will become 1509.8 kilojoule per minute. So please do the calculations at your home, and you come to know this particular answers correct or not. So this is something about the solution of this particular first problem. So after this one, now we are going to discuss the another problem. So again the statement is very important. The following observations were recorded in a test of 1 hour duration on a single cylinder oil engine working on 4-stroke engine. So this is again very important. So there is a 1 hour test is there, and the engine is 4-stroke engine, and oil engine is there, single cylinder oil engine is there. So the bore is given, that is equal to 300 mm, stroke is equal to 450 mm, fuel used is equal to 8.8 kg, the calorific value of fuel is equal to 41800 kilojoule per kg, average speed is given in the problem, that is equal to 200 rpm, mean effective pressure is equal to 5.8 bar, net brake or brake friction load is equal to 1860 Newton, quantity of cooling water is given 650 kilogram, temperature rise is equal to 22 degrees Celsius. So the diameter of brake wheel is again given 1.22 meter. So with the help of this given data, we have to calculate first the mechanical efficiency, then the brake thermal efficiency, and in this problem we have to draw a heat balance sheet. In the earlier problem they have not asked to draw the heat balance sheet, only they wanted to get the answers of this particular unknown, brake thermal efficiency, indicated power, brake power, etc., etc. But in this problem they want to get the heat balance sheet. So here there is a need to understand how we can get or how we can draw the heat balance sheet. So again the things are given, single cylinder engine is there, that is the small n is equal to 1, and the bore diameter is also given, that is equal to 300 mm converted into meter, so that would be 0.3 meter. The stroke length of the engine is again given in terms of mm, so convert it into meter, that would come 0.45 meter. The mass of fuel is also given, that is 8.8 kg per hour. Calorific value is given, that is 41800 kilojoule per kg. So dear friends, as per the given data, as per the statement of the problem, here I have written the things in given data. Okay, so the calorific value is 41800 kilojoule per kg. RPM of the engine, that is equal to 200, that is 200 RPM. The indicated mean effective pressure, that is equal to 5.8 bar. This is given in the problem. Brake friction load, which is given as 1860 Newton. So this is the term, the net brake or brake friction load, which is given in the problem. So in the last problem, W1 minus W2 we have referred, and that 150 minus that 30, and we got that 130. Okay, so but in this case the no W1 and W2 is given, the direct net brake load or brake friction load is given, and which has to be considered 1860 Newton. Again, there is no conversion of multiplying 9.81 because the load is given in terms of Newton itself. Okay, so directly this brake friction load we can consider sometime W minus S, that is for net brake loads formula. Sometimes we can use W1 minus W2, sometimes we can use W minus S. So again here there is no need to calculate that one because the brake friction load is directly given, and that is equal to 1860 Newton. So the mass of that particular cooling water jacket is also given 650 kg per hour. So that M suffix W, which is given in the problem, quantity of cooling water 650 kg, and this is for hour basis. So all these values are for per hour. That's why we have written over here 650 kg per hour. So again the temperature rise is given, that's why we have to consider, sometimes we can write T2, or sometimes we can use TW2 minus TW1, or sometimes you can use T2 minus T1, like that. So nothing to worry about this indication. So that would given as 22 degrees Celsius. So the brake wheel diameter, it is also given. Sometime if we want to use the indication D suffix B, that is for brake wheel diameter, and it is equal to 1.22 meter. And the value of K, as we know, the for 4-stroke engine the value of K is 1 by 2. So after this one, now here first of all we have to calculate the mechanical efficiency as per the different things which we have to calculate in this particular problem. So we have the formula brake power divided by indicated power into 100. So for the mechanical efficiency, we don't know what is the indicated power, we don't know what is the brake power. So one by one we can calculate this particular thing thoroughly. So the first one, that is indicated power, we know the formula of it, N into P suffix M I into L into A into N into K into 10 by 6, and the value will come in kilowatt. So all the things are given in the problem. The number of cylinder is 1, PMI value is 5.8, the stroke length is given 0.45, area that is pi by 4 into d square, the diameter is 0.3, the N value is 200, the K standard value is 1 by 2, and into this 10 divided by 6. So we can get the indicated power is equal to 30.75 kilowatt. So similarly, the next one, that is the brake power, and that formula is 2 pi nt by 60 into 1000, and it comes of kilowatt. So again the torque is unknown, so we have to calculate the torque. So the torque formula is again W into R. So the load is given directly W minus S, in the last formula W1 minus W2 we have considered, and into multiply by 9.81. But in this case, that particular W minus S, which is directly given in the problem, that is equal to 1860 Newton. So directly we can put the value over here into the brake wheel diameter is 1.22 divided by 2, that is nothing but the radius. So after calculation we can come to know the torque is equal to 1134.6 Newton meter. So put this value in the equation of brake power, and finally we can get the brake power is equal to 23.76 kilowatt. So here we have the brake power and indicated power with us. So put both the values in the equation of mechanical efficiency, and we come to know the mechanical efficiency is equal to 77.27. So this is the first unknown. So to calculate the mechanical efficiency, we have to calculate first brake power and as well as the indicated power. So the second unknown is the brake thermal efficiency. So again we have the formula brake power divided by mass of fuel into calorific value into 3600. So why this particular 3600 is here, we already discussed in the earlier problem. So the same thing is I am not going to repeat over here. So the brake power we have calculated over here 23.76, mass of fuel is given 8.8 kg per hour, the calorific value is 41800 into this 3600, and we come to know the brake thermal efficiency is equal to 23.25%. So after this one, now we are going to discuss about how to draw the heat balance sheet. So for heat balance sheet, so we already discussed the theory calculation of heat balance sheet. So with the help of that theory calculation knowledge, we are going to use this particular heat balance sheet. So first of all, in the case of heat balance sheet, we have to calculate the heat supplied by fuel. So what the total heat supplied by the fuel? So we have the formula. So this is the gas engine. No, this is the oil engine or petrol engine. Yes. So we have the formula of QS. QS is equal to heat supplied by fuel is equal to mass of fuel into calorific value. So the mass of fuel is given, calorific value of fuel is given. So put that values over here and we come to know the heat supplied by fuel is equal to 367840 kilojoule per hour. So all the values are given on hour basis. That's why we are going to draw the heat balance sheet on hour basis itself. If it is given in the minute basis, then you can able to calculate the values in minute basis. If it is in second basis, then we can able to calculate the things in second basis. So here we are considering the hour basis. So we come to know the total heat supplied by the fuel in this problem is 367840 kilojoule per hour. So this is the total heat supplied by the fuel. So now similarly the first one we have to calculate in this particular heat balance sheet, heat absorbed in indicated power. We have the formula indicated power into 3600. This 3600 for the hour basis. So these all things are on hour basis. So there is a 3600 seconds in hour. That's why we have to multiply this particular thing. So indicated power into 3600 and that would come 110.520 kilojoule per hour, that is heat absorbed in indicated power. Similarly, the second one, heat carried away by cooling water. We know the mass of cooling water into specific heat of the water into this T2 minus T1. So we can consider the standard values of specific heat of water. Sometimes it is given in the problem. If it is not given in the problem, so we have to consider these standard values also. So after putting all the values over here, we come to know the value is 59774 kilojoules. So this is the heat carried away by the cooling water. So after this one, the next one, that is heat unaccounted. So how we can calculate the heat unaccounted? Heat supplied minus summation of 1 plus 2. So if you observe over here, we are not going to calculate the third unknown, that is heat carried away by the exhaust gases. Why we have not calculated that particular thing? So my dear friends, in this particular case, nothing is given for the exhaust gases. If you read the problem thoroughly, there is no any kind of data is given for heat carried away along with the exhaust gases. Nothing is given or nothing record is available in the statement of the problem. Yes, for the quantity of cooling water it is given 650 kg, but there is no any kind of a heat during the exhaust gases is mentioned in the problem. So we have neglect that particular thing. That's why only we have considered the heat carried away by the cooling water. So according to the given data, we have neglect that thing. So similarly, when we are going to calculate the heat unaccounted, that is total heat supplied minus the summation of this 1 plus 2. if we calculated that third point, that is heat carried away by the exhaust gases, in some problems the exhaust gases data will also provide. That time we have to calculate that calculations also, or that value also. That time this formula would be 1 plus 2 plus 3, but here is no third term is there. That's why this heat supplied minus summation of this one heat absorbed in indicated power plus heat carried away by cooling water. So we come to know this will come 197546 kilojoule. So this is all terms are in our basis. So now we are going to draw a heat balance sheet on our basis. So again we have to write these things, heat balance sheet on our basis. The first column indicates the atoms as we already discussed in that particular theoretical bit. So the second column indicates the kilojoule. This is about for the heat, and this is about the percentage value in the percentage. So as we just calculated the total heat supplied, that is 367840. This is total heat supplied. So we can say this is the 100% heat which is supplied by the fuel. So you just write this thing. So 367840, that is heat supplied by the fuel, and this would be 100%. Let us consider. So the first point, that is about the indicated power, heat absorbed in indicated power, that is 110520, and the heat carried away by cooling water is 59774, and the heat unaccounted is 197546. So put all the values, first, second and third. Here is 110520, 59774, and third one 197546. So if 367840 is 100%, then for this value, what about the percentage of 110520? So that will come 30.0% against 100% of heat, against this particular amount of heat. Similarly, this 59774 is nothing but 16.25% of that total heat. Similarly, 197546 is the 53.70% of total heat. So if you observe over here, this is about for indicated power, this is about the cooling water, and this is about the total heat unaccounted, and this percentage is higher than this both percentage. So if you make the summation of the 30.04, 16.25 plus 53.70, it will come 99.19%. And again, if you calculate, if you make the summation of 110520 plus 59774 plus 197546, that would come 367840, and these both terms, this term and this term, both are equal to each other. Similarly, this 100% and this summation is equal to each other. So this summation and this summation, if you see, we can say, we can just cross check the things, and we can say whatever answers we have calculated are exactly correct one. So this is nothing but called as a heat balance sheet on our basis. So I hope you understood this particular both the problems on this engine testing and performance analysis. So one more thing which I forget to tell about the calculation part of this heat carried away by cooling water. As we already discussed, the formula is the M suffix W, that is the mass of cooling water or the jacket of cooling water, into the CPW. CPW is nothing but for the specific heat of water multiplied by that T2 minus T1. So in this problem, the general value of CPW, which sometime it is given in the problem, or if it is not given in the problem, so always remember, dear friends, the standard value of CPW is equal to 4.18 kilojoule per kg degree Kelvin. So just put this particular value in this equation, and the mass of cooling water, which is already given in this particular problem, and that value is given, and which is equal to 650 kg. So this is for our basis. So the quantity of cooling water is given in the problem is 650 kg. So put that 650 over here, and the temperature difference is also given in this particular problem, and that value, it would be, I think that is given is 22 degrees Celsius. So we can convert this into degree Kelvin. So put all that values over here, and finally we come to know the answer will be 59774 kilojoule. So similarly in the earlier problem also, where we have to calculate that heat carried away by coolant in the earlier problem, as we already discussed. So here is also the CW value, that is a specific heat of water, is not given. That time we have to consider the standard value, that is 4.18 kilojoule per kg degree Kelvin, and accordingly put the given values, and then we can get the answer would be 1509.8 kilojoule per minute, or sometime it would be 1504.8 kilojoule per minute. So please do the calculations at your home. So I hope you understood this particular all things thoroughly. So thanks a lot for watching this session.